Good afternoon. Welcome to Krishna's class. Recall our last lecture. We introduced the AM, or we started with the GM-AM inequality. That means geometric mean, arithmetic mean inequality, a classical inequality for numbers. And then we reformulated the whole thing in a situation suitable to study the measure and integration environment. And this led to the so-called Jensen's inequality. It was actually working back, the sums were replaced by integrals, etc., etc., and then we got into the standard form of the Jensen's inequality. Therefore, Jensen's inequality is in some sense a generalization of the arithmetic mean or geometric mean, arithmetic mean inequality. Okay. So having seen that, I think I have already stated the theorem, which I recall again or put it over here. So let me just read that, Jensen's inequality. The statement of the theorem is as follows. Let omega scriptem mu be a measure space. That means omega is the set, scriptem is the sigma algebra, mu is the measure, such that mu of omega equal to 1. That means the measure mu is such that mu of omega equal to 1. Which, in other words, we are talking about probabilistic measure. Let f be a real valued function on omega, which is in L1 mu. So you are talking about an L1 mu function on omega. It's a real valued L1 mu function on omega. And let f be bounded by a and b. That means a less than fx less than b. That means the lower bound is a, upper bound is for every x belonging to omega. And let now phi be a convex function on AB. Then phi composition, the integral over omega of f is less than or equal to integral over omega phi composition f dv. Okay, so this part, you see, integral f d mu is mu of omega is equal to 1. Therefore, you see that this lies between a and b. Therefore, phi is well defined. So the left hand side is well defined, and the right hand side is, of course, you are taking phi composition f as a function of x, then integrating this function of x with respect to mu over omega. Okay, so this inequality now let us prove this result. And remember, we have phi is a convex function, and you will see this particular property of convexity of phi playing a crucial role in getting this inequality. And that's why in the general theorem we were using exponential. See, when we considered that example, we were in the For phi, we were using the phi that appeared there was exponential function, which is a convex function. Okay. Therefore, naturally, you would suspect that is it not true for all choice of phi? But then you see that it is an important ingredient in the proof of this inequality that phi is a convex function. I will make some remark on this statement. The case A equal to minus infinity, B equal to plus infinity are not excluded. That means fx could be lying between minus infinity and plus infinity, or f could be any real valued function. In such cases, phi composition f may not be L1b. Okay, so you are working on omega, and this may not be an L1 mu function. And then in such cases, G mu exists in the extended sense. And has value. Yes. Now that's of course a special situation where this may not be necessarily valid in that case. Okay. Now we give the proof of this theorem. We recall one of the inequalities that is valid for a convex function. Given that phi is convex, implies okay. What does this mean? The meaning of this is, if you explore, see, the function phi that you have is something that bends upwards. Okay, see, defined on the interval a, b, and then this is a function which has bends upwards. I mean, how does this come? So you take a point T. And now I'll just give the inequality is valid for A less than S less than T less than U less than. So you have got T here and S is here and U is here. Okay. So phi t minus phi s, suppose this is the function. Suppose this is the function t phi tau. That is phi t. Then this is the height phi t, and here it is phi s, and here it is phi. Now it simply says that what you are getting is the slope of this line. This is phi t minus phi s divided by t minus s is this slope of this line segment, and phi u minus phi t divided by u minus t is the slope of this segment. So you have two segments here. So it simply says that these two, the slope of this is greater than or equal to the slope of this portion. So that means the function is convex in the sense that it bends upwards. Okay. As you go further and further to B, it bends or it grows more sharp. That's the meaning of it. Okay. So this inequality is at the back of our argument. Let me retain the theorem there and work. So we in fact make use of the above inequality in our work. How do we do that? Take t equal to integral over omega ft. Then we have mu of omega equal to 1, and therefore this is equal to, this gives the inequality a less than t less than q. Suppose beta is supremum of where less than t, then beta is no larger than quotients. Minus t. For u belonging to okay. That's the part I have explained earlier. Okay, and we have a a less than s less than t less than u less than v. Now it follows that phi s is greater than or equal to it comes from this inequality. Okay, from this inequality, because this is less than or equal to beta, and therefore phi t yeah, so you can work this out easily, right? So this is true for a therefore this implies phi of s you write as fx. Phi t is so you are writing s is equal to this is the choice thing. That is phi of fx is greater than or equal to and you have this relation, you can rewrite the whole form in this particular form. It is just read this same statement rewritten. Okay, so this is or you can put it in this form. Equal to 0. Now observe that y is continuous. We have proved this already, that if phi is a convex function, then it is continuous. Okay, and that implies, which implies the previous theorem. I mean, the beginning of the, not in the last lecture, but in the previous one, we have proved that phi is necessarily a continuous function. It's convex. Okay, and this implies you take phi composition F. You are taking a measurable function with a continuous function. So this is measurable. This is measurable. Therefore, you can integrate this above inequality over omega. Therefore, you have integral over omega this is greater than. Now phi t plus beta into fx minus t fx. Therefore, integral over omega is less than or equal to integral dv. And one side of the inequality comes that way. Okay. Now put t equal to then what you have is integral over omega Now this is these two cancel, and this is was less than or equal to okay, so we are using this. This side we have evaluated, and the left hand side is equal to this, and the right hand side is this. Okay, so this inequality. Okay. Therefore, from start, we have integral over omega integral over omega. What is this? This is therefore what do you get? Therefore we obtain phi of d mu. But this is equal to 1. This implies so that is the Jensen theorem. That completes the proof of the theorem. The last time we have explored how we get this GM-AM inequality. Okay, and you can derive several inequalities from this, because what happens is that for every choice of a convex function phi, you have a corresponding inequality, and from this one can derive from the Jensen series. The GM-AM mean, what you mean by the geometric mean, arithmetic mean, one among them. Now the choice that you make is pi x equal to e power x, which is an exponential function. Now you see, you can, therefore you get exponential of integral over omega is less than or equal to Now we have a lot of things that you can choose. You can choose not the phi, you can choose f, you can choose, and mu you can choose. Sorry, omega you can choose. So what we do is we make the following choices. Yes. Some n real numbers. Now mu of Pi equal to 1 by n. So you also take f of pi xi, which is non-negative, for each I. Then you get exponential of sigma. Integration gets replaced by sigma here. Fpi is less than or equal to 1 upon n this if you rewrite, you get exponential of 1 by n So you write e to the power xi by n. Then we have y1 yn to the power 1 by n with this substitution you actually find out what it is. You get yi equal to or xi equal to log yn. Substitute that and then write it up. You get this. So that's the proof and an application of this. And in fact, as I said, that several choice of phi can be made, convex functions, and f you can choose, omega you can choose, the measure you can choose, etc. So with that, a variety of inequalities to suit each situation can be manufactured. So that's the advantage of this inequality. So it is very, very gentle. Thank you very much.